Okay, so this one's a goodie. Calculate the average distance between the excess electrons on one plate of a parallel plate capacitor, for which the plates are separated by 1.00 millimeters of air and have a potential difference between them of 1.00 times 10 to the 3 volts, or 1 kilovolt. Okay, where do you start there? Let's just quickly revise what's happening with the capacitor, and then we'll look at how we might approach this. So, parallel plate capacitor, if you consider the one plate's going to be charged up by having electrons put on it, one's going to have electrons removed from it. This one becomes positive, this one becomes negative. So we're looking at the average distance between the excess electrons on one plate, for which the plates are separated as excess electrons. So we might, I think we'd be right in assuming that we're dealing with the negatively charged side. Okay, and so we've got a whole bunch of electrons on the plate. You would assume that they evenly distribute themselves to be as further apart from every other electron nearby it. So you could imagine that it creates a sort of a grid with electrons at the points, or maybe a little bit easier, electrons right in the center of each of those grid squares. So the distance between any two electrons should be the same as the distance, or the length of one side of one of these squares, so just that one small length there. Okay, so what we have to do is find out the number of electrons on a particular area that is known. Once we know that, we can then work it out, because we would take that area and we'd divide it up to say like if it was a meter square. 1 divided by the number of electrons should give us the amount of square meterage per electron, which we can then take the square root of to find the side length. Okay, so that's kind of working backwards a little bit. How do we get to that? Well, we're told the voltage, so we know V. We're told the distance of spacing. And earlier on we're given the absolute permittivity of free space. We don't need the dielectric constant because it's air. So it might be a good idea to start from the capacitance formula. So capacitance is absolute permittivity of free space times the area divided by the distance. We have the distance separation, we have that. We don't have the capacitance, we don't have the area. Okay, but we do have another formula we can throw into the mix. Q equals CV. We have the voltage, we still don't have the capacitance, and we don't have the charge. Ultimately we're aiming for the charge. So we work out the charge on the plate. We can divide that by the charge on a single electron, which is 1.6 times 10 to the minus 19 coulombs, or negative 1.6, and that'll give us the total number of electrons, which is what we stick in on our fraction here, 1 over, well, there we go. We can just say, take a test area of 1 square meter. So if we make that area to be equal to 1 meter square, or 1 meter square, and this is like per meter, if you like, capacitance per meter, so that'll still be enough to give us the spacing of the electrons. The other thing we could do is take a test charge and say the test charge is the charge on one electron, and then use that to rearrange and find the area required. But in any case, I've skipped ahead just a little bit. We can come up with an expression for Q by multiplying the top one by V on both sides. So that should equal Q. And again, we know V. So now we actually know everything if we assume we're dealing with 1 meter square to find the charge per meter. Okay, followed that? So we've set it at 1 meter square, so the area at 1 meter square, so that means we can find the charge per meter. Then we can take our 1 meter and divide it by the number of electrons, which we've worked out from the charge divided by the charge on a single electron. So this charge here is the total. So I'm not going to do that, because this is actually how they did it in the answers. So I'm just going to kind of give you a few figures along the way. So for the capacitance they work out for 1 meter square works out to be 8.8954 times 10 to the negative 9 farads, So that's 8.8954 nanofarads. So that's one thing that's calculated. And then from that you can multiply by the voltage to find the charge. So the charge that they work out is, and since it's 1 kilovolt, that's easy. It's 8.8954 times 10 to the minus 6, and it's coulombs. Okay, so then we have to divide that total charge worked out by the charge on a single electron, and that gives us the number of electrons so electron number is 5.560 times 10 to the 13. It's a lot of electrons. A lot of electrons indeed. So now we've got the number of electrons, we can find out the area per electron by doing 1 divided by the number of electrons. So the area per electron is 1 divided by 5.560 times 10 to the 13 gives us 1.80 times by 10 to the 14 meters square, because remember this is the area per electron on one of those small ones. We're going to have to take the square root of that to find the actual area, to find the actual side length of one of those area blocks, and the side length should be equal to the spacing between the electrons. So the square root of the area, gives us 1.34 times 10 to the negative 7, sorry, that 7 would be rather large, 1 electron per kilometre. No, 1,000 kilometres, 100,000 kilometres, 10,000 kilometres, anyway. And that is in metres. So that is the spacing between subsequent electrons, or electrons on this sheet. It's pretty incredible. So this is per metre. So it doesn't matter what your actual area of the capacitor plates is. This is the test charge per metre, because remember, in the centre one, if we divided both sides by, instead of using that area of 1 metre, if we divided both sides by area, we would cancel that out, and this is the number of charges per metre, because we can set A to be 1, so it's per 1 metre square. So it's a kind of a test charge. It's a little bit like electron volts and things. You say 1 volt and you set it up and define it as that. So anyway, that's a charge per metre. Okay, awesome.